What if the real key to our energy future isn't up in the sky, but, well, deep, deep beneath our feet?
It's an intriguing thought, isn't it?
Yeah, and for everyone tracking energy transitions especially, UPSC aspirants preparing for exams, finding sustainable power is critical.
Absolutely.
So today we're taking a deep dive into something called ultra-deep geothermal energy. It's potentially, well, almost limitless.
It really is. The amount of heat energy stored inside the Earth is just vast. For a long time, getting at it, especially at those really extreme depths, seemed almost impossible.
Like science fiction?
Kind of, yeah.
Yeah.
But the information we've looked at shows there's some serious progress being made, real breakthroughs.
Okay.
So this deep dive, we're going to explore how these cutting-edge advancements are making this resource look much more like a viable option, for a cleaner, more secure energy future.
Which is exactly the kind of forward-looking topic crucial for, say, UPSC current affairs prep.
Precisely. Understanding these future energy trends is vital.
Right. So we've looked at materials explaining the basic science and some really groundbreaking tech developments.
We have.
Our mission today is pretty clear. Really get our heads around the potential here and the key technologies making it happen. Okay, so let's start unpacking this. Why now? Why is tapping into Earth's deep heat suddenly getting, well, so much attention?
Well, look at the current energy picture. Even with all the growth in solar and wind, which is great,
Yeah, impressive growth.
we're still heavily reliant on fossil fuels. The data really underscores that.
Still the backbone, unfortunately.
Exactly. And geothermal, particularly this deep kind, offers something really compelling. It's dense energy, it's consistent, runs 247, and crucially, zero carbon emissions, no radioactive waste.
That consistency is a big deal compared to renewables that fluctuate.
It is. And the potential scale, it's kind of mind-blowing.
I remember seeing a figure that really jumped out.
You're probably thinking of the International Renewable Energy Agency estimate.
That's the one.
Yeah, they estimate the technically recoverable potential is more than 10 times the world's current electricity demand.
10 times.
Yeah.
Just think about that. For those of you mapping out global resources for, say, the UPSC exams, that scale is enormous.
It really dwarfs our current consumption potential. And as you said, unlike wind and solar, it's stable, continuous.
Always on, which is, gold dust for energy planners trying to guarantee that baseload power.
Exactly. It's a perfect complement, really.
Yeah.
But the big but has always been getting down there, accessing those deep heat reservoirs efficiently and affordably.
Which brings us to the huge engineering hurdles, right? The physics of the deep.
Mm-hmm. It's a completely different environment down there.
So what makes it so tough? What are the big obstacles?
Well, two main things. Pressure and temperature. They both ramp up dramatically the deeper you go.
How much pressure are we talking?
The pressure goes up by about 3,600 pounds per square inch, roughly, for every kilometer down. Think Mariana Trench kind of pressures, but combined with intense heat. And the rock itself, it changes. Near the surface, it might be brittle, easy to fracture.
Right.
But deeper down, under that heat and pressure, it becomes more ductile, pliable, almost like really stiff clay.
So it wants to flow, to squeeze the whole shot.
Exactly. Maintaining an open borehole becomes incredibly difficult. Plus, the heat.
Yeah, let's talk about the heat.
We're aiming for zones that are between, say, 570 and maybe over 930 degrees Fahrenheit.
Okay, that's incredibly hot. What does that do to the drilling equipment?
It causes all sorts of problems. Drill strings, the long pipes can buckle under their own weight and the stress. Drill bits wear out incredibly quickly.
I remember reading about the Soviet Kola Super Deep project.
A classic example. Took them decades to get just over 7 miles down. It really shows the limits of traditional drilling.
And conventional rigs, they sort of hit a wall around 6 miles deep anyway.
Pretty much. And think about the electronics, the sensors you need down there to know what's going on.
Yeah, they wouldn't last long at 900 degrees F.
Not at all. The heat just fries sensitive components, melts seals. So yeah, conventional methods just aren't cut out for this ultra deep stuff.
We need something fundamentally new.
We do. And that's where some of the really exciting innovation comes in. One key concept is using something called supercritical water.
Supercritical water. Okay, that sounds very sci-fi again. What is it? Why is it a game changer?
So water becomes supercritical when you heat it above about 703 degrees Fahrenheit and keep it under pressure, above roughly 3,200 psi.
So conditions you'd find deep down in these geothermal zones.
Exactly. And in that state, it's weird stuff. It's kind of like a liquid and a gas at the same time. It has the density of the liquid, but flows easily like a gas.
Okay. But why is that useful?
The big thing is energy density. Supercritical water can carry much more heat energy than regular liquid water or steam, dramatically more.
How much more are we talking?
The potential is maybe increasing the power output of a geothermal plant by up to 10 times.
10 times. From the same amount of fluid, basically.
Effectively, yes, because the enthalpy, the total heat energy it carries, is almost double that of normal high-temp steam. This means you need less fluid flow for the same power output.
Which means less energy needed for pumping, lower costs.
Precisely. It makes the whole process much more efficient. A tenfold boost isn't just improving things, it's potentially revolutionary. It could make geothermal a real, heavyweight contender against traditional power sources.
Nuclear scale power from a geothermal plant. That's the idea.
That's the potential, yes, with a much smaller environmental footprint.
Okay, so supercritical water is the goal. But we still need to get down there to access it. Back to the drilling problem.
Right. And this is where we see some fascinating tech. Let's talk about microwave drilling first.
Microwaves. Like, in my kitchen, how on earth do you drill rock with microwaves?
Yeah, it sounds odd, I know. But a company called Quaity Energy is doing just that, instead of a physical drill bit grinding the rock.
Which wears out constantly.
Exactly. They use a special waveguide, like a 3-inch metal tube, to beam high-power microwaves up to a megawatt directly at the rock face.
And what happens?
It basically vaporizes the rock. Granite, basalt, whatever's down there. It turns it into plasma and vapor, clearing the path without physical contact.
No physical contact, so no bits to replace.
That's the key advantage. It eliminates one of the biggest costs and causes of downtime in deep drilling. Makes the economics look much, much better.
Have they actually done this?
They've done successful plasma tests, at Sandia National Labs. Their plan is pretty ambitious, a 3-mile deep well by 2026, and then a 100-megawatt pilot plant by 2030.
Wow. That could really change the game for geothermal.
It absolutely could. It offers a potentially much faster and cheaper way to reach those ultra-deep, super hot resources.
Vaporizing rock miles down. Yeah. Amazing. Okay, what else? Are there other new drilling approaches?
Yes, another really interesting one comes from Fervo Energy. They're adapting techniques from a different industry, the shale oil and gas sector.
Horizontal drilling, fracking. How does that apply here?
Sort of, but geothermal style. They drill down maybe about 8,000 feet or so, and then drill horizontally, sometimes multiple horizontal wells intersecting each other.
Okay.
Then they use high-pressure water, yes, a bit like fracking, to create a network of small fractures in the hot rock between these horizontal wells.
Ah, I see. To increase the surface area.
Exactly. Creates a much larger area for the water circulating through the system to pick up heat from the rock.
Smart. But how do you circulate the water? Pumping at those depths must be hard.
This is the clever bit. They often rely on the thermosiphon effect.
Thermosiphon?
Yeah, it's just natural circulation. Cooler, denser water sinks down one well, gets heated by the fractured rock, becomes hotter and less dense.
And rises naturally up the other well.
Precisely. No need for deep, energy-hungry pumps down in the hottest zones. Nature does the work.
That's elegant. Has Fervo had success with this?
They have. Early pilots in Nevada hit about 3.5 megawatts, and they have a test site in Utah that's reached really high temperatures, 752 Fahrenheit, aiming for potentially 90 megawatts.
90 megawatts?
Yeah.
That's serious power. Enough for, hundreds of thousands of homes?
Yeah, potentially over 400,000 homes. And what's also significant, especially for scaling this up,
yes,
they're using existing oil field drilling rigs. They don't necessarily need brand new specialized equipment for the drilling itself.
Which means it could be replicated faster, potentially across wider areas.
That's the idea. They estimate areas with suitable hot crust could cover maybe 70% of the continental U.S. So, yeah, potentially widespread adoption.
Okay, so we have innovative drilling like microwaves and horizontal fracking. Yeah. Are there other improvements happening, maybe in how the whole system operates?
Definitely. There's work on efficiency and sustainability, too. Some startups are looking at closed-loop systems.
Closed loop, meaning the fluid doesn't touch the rock directly?
Right. The working fluid circulates inside sealed pipes, like a giant underground radiator. It picks up heat through the pipe walls.
What's the benefit of that?
The main thing is avoiding mineral scaling. When hot geothermal brines flow directly, they can deposit minerals that clog up pipes and equipment. A closed loop avoids that completely.
Makes sense. Keeps the plumbing clean, basically. Anything else?
Yes. There are experiments combining geothermal fluids, the brines, with supercritical carbon dioxide.
CO2. Why add that?
It seems to improve how the fluid flows and extracts heat. And interestingly, it offers a way to potentially sequester CO2 underground as part of the process, turning a problem into part of the solution.
Double benefit.
Clever. And another really pragmatic idea is hybrid plants, repurposing old coal power stations.
How'd that work? Keep the buildings but swap the fuel?
Essentially, yes. You'd replace the coal burners with geothermal heat exchangers, but keep using the existing turbines, generators, cooling towers, grid connections, all that expensive infrastructure.
So you leverage sunk costs and just switch the heat source. That sounds like a potentially smoother transition pathway.
It could be. It makes the economics look better and uses assets we already have. A way to shift from fossil fuels more seamlessly.
Right. So we've gone from this huge untapped potential deep underground through the really tough challenges to these, frankly, amazing innovations in drilling and energy extraction.
It does feel like we're on the cusp of something significant, doesn't it?
It really does. This ultra-deep geothermal, it holds out the promise of stable, abundant, clean power.
Yeah. Now, there are still challenges, let's be clear. Managing induced seismicity, tiny earthquakes caused by fluid injection in some areas needs careful handling.
Right, that's always a concern with subsurface injection.
Improving the long-term cost-effectiveness of these new drilling techs at scale is still ongoing, but the direction of travel, the pace of innovation, it's very, very encouraging.
So the really big question then, for everyone listening, and especially for you UPSC aspirants thinking about long-term energy policy, is this. As these technologies keep improving, could ultra-deep geothermal become, a cornerstone of our renewable energy future?
It's the key question. To wrap up our deep dive today, we've seen the almost limitless energy potential miles beneath us. We've touched on the extreme conditions, the heat, the pressure that make it so hard to read.
Yeah, the sheer difficulty.
But then we looked at the breakthroughs. Supercritical water boosting power output tenfold. Microwave drilling vaporizing rock. Horizontal fracking creating huge underground radiators. Closed-loop systems improving reliability.
It's a whole suite of innovations converging.
Exactly. And these developments are incredibly significant for building a sustainable energy system and, finally moving away from fossil fuels.
Absolutely. For anyone preparing for the UPSC, understanding these emerging trends in energy tech is vital. It touches on energy security, environmental policy, technological leadership, key themes for the mains exams.
Definitely. And the information we discussed today draws heavily from reporting found on sustainable.com. We really encourage you to check out their site for more details and do your own further reading.
Yeah, do dig deeper. And for all of you listening, whether you're deep in UPSC prep or just fascinated by where our energy might come from next, if you found this useful, please do hit like and subscribe. It helps others find the discussion.
And leave us a comment. Let us know your questions or if there are other related areas you'd like us to explore.
Yes, please do. So we'll leave you with this thought. In a world searching so hard for clean, reliable energy, could the answer have been right under our feet all along, just waiting for us to figure out how to unlock it?